All right, so today we'll be doing the heat transfer assignment we have due tonight, and so let's start. So we have given in an industry based on, so let me just quickly pull up lecture 12. All right, so we have over here. So we're given the dimensions of a two pipes, 145 and 95 millimeters, and they're spaced 0.6 meters apart, and they have temperatures of 168 and 6 degrees respectively. It's found through reliable measurements, so the measurements are not faulty, that the heat transfer rate between two pipelines is 142 watt per meter length. It is believed that there is a large discrepancy between the predicted Q prime calc and the measured Q prime measured heat transfer rate. Calculate the theoretical heat transfer rate between two pipes using conduction shape factor using a technique that we are studied in lecture 12. So this is part A. Part B is what are the possible technical reasons for this discrepancy between the calculated and the measured values of Q prime, and then from the technical reasons formulate a solution plan describing a potential outcome of a solution. So let's just describe what we have over here. So we can draw, for example, a pipe and then a smaller pipe. All right, so we go now down to get rid of this circle option. So the distance between the center is W is 0.6. So W equals 0.6 meters. Now the diameters of this circle is D2 is 0.095 meters. The diameter of this pipe is 0.145 meters. Okay. The T1 here is 168 degrees at the surface, right? Surface temperature. And T2 here is 6 degrees. Okay. So now we have drawn the model. Now one more thing that we have to also assume here is K soil is 0.5 from the slides, watt per meter Kelvin. Okay. So that's just a schematic of the problem. Now we can try to solve this. Now before we solve this, we need to state some assumptions. So the assumptions that we can state, these are the same assumptions that we have given to us in our lecture slides. So just to remind you, so we have our steady state conditions. Conditions. We also have our 2D conduction, and we also have your typical constant properties. All right. To assume the shape factor, we also have to say that to assume the shape factor that's in the lecture slides as well. The assumptions that we're going to take is shape factor assumption. Shape factor would be the pipelines we're assuming are buried deeply, deeply, so we can approximate using the case 4 in table 4.1, which is in the lecture slides as well. Okay, another thing we can also mention is that this is more common sense, is that the pipe length has to be larger than the diameter, right? Okay. Another thing is this spacing has to be larger than the diameter itself, d1. Okay, so these are our assumptions done. Now we can proceed to calculating what's going on over here. So q prime, let me get rid of text box. So q prime is it's q over l, and q over l is our shape factor s over l multiplied by k soil times by delta t, which is t1 minus t2. Okay, so to find the shape factor of case 4, that's given to us as pi 2 pi l all over cosine h inverse of 4w squared minus d1 squared minus d2 squared all over 2d1 minus, sorry, d2. Okay. Now you'll notice we're after s over l. So we can rearrange this to say S over L equals 2 pi cos h inverse. Now I'm going to substitute the values in, so 4 times 0.6 squared minus 0.145 squared minus 0.095 squared all over 2 times 0.145, 0.095. Okay. So our S over L should be, so our S over L should be over here, and it should be around, so I'll check. So for this will be, for me it's options, for me it's on the other side. Hyperbolic, I need cautious inverse before this, I need sets of fraction. So 2 shift pi for me, and then okay, need a bracket. So for me it's 4 times 0.6 squared minus 0.145 squared. Take away 0.095 squared all over 2 times 0.145 multiplied by 0.095. All right, and we should get a value of, so we get a value of around 1. So we could, I'm just going 1.357, and then it keeps on going. Okay, that's our S over L. Now we can work out Q prime. So Q prime is equal to 1.357 dot 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 multiplied by K soil, which we're assuming 0.5, and times by the temperature difference of 168, take away 6. So we should get, let's check. That's the answer times by 0.5 times by brackets 168, take away 6, and we close the brackets, press equal. We get 1109.96 watts per meter, watts per meter, watts per meter, meter length. Okay. So the value we should get is around 142. So comparing them, we're off by 30, right? Which is quite a big margin. So let's look at part B now. Let's add another page here. What are some of the technical reasons that we could have done something that we could change here, or at least let's first identify them and then we'll look at some solutions. So some assumptions we did, right, initially. Okay, I'm going to type this up now so it's easier to just see. So we assume the K value, right, with the assumption. So number one, assumed K value, or maybe not K, but let's write, let's be more specific, thermal conductivity of the soil may not be accurate. So that's our one possible discrepancy, technical reasons. Also the temperature variation, temperature variation at the surface may have occurred, due to what? Transient conditions, which is leading to a different, so leading to a different final answer in the steady state assumption. Okay, number 3. And we also can look at, we assume that it's buried deeply, so the depth here, depth could affect, we don't know, could affect the heat dissipation occurred. Okay. Now we're assuming that the measurements are reliable, but there could be an uncertainty due to sensor placements and calibration errors. Okay. Now that's it. Sorry, not 2 again. That's 3, and this is 4. Now you don't need to go much in detail, but I will later. But for those who are interested, but for now, This is enough. So let me just go back here. This is enough. So now let's go and write over here. This is part C. Okay, part C. So how can we assume a better K value for the soil? So what we can do here is over here we can say that conduct. So we can conduct a soil thermal conductivity test test to get a more accurate value of K. Now, how can we do this? We can do this by thermal probing, thermocoupling the thermal probes, right? To test the measure to test to measure, sorry, soil conductivity. We'll have like a data acquisition system like we did in our experiment. So we'll log it and tabulate our answers at different temperatures. So different temperatures to to get a K value from the K value from the gradient. So for example, if I was to draw a plot, so let's go here, Control Shift P, let's draw a plot. So draw a coordinate axis. So for example, let me just draw a coordinate axis here. So let me just draw, where's my pen again? There we go. Okay, so let's draw a plot here. And we can say that our plot is, for example, uh, against time, so different temperatures, right? And our x-axis is, for example, the power, right? The power is power in watts. Power in watts. Now, we know the power is the rate of change of our heat transferred. So del Q over, sorry, Q over del T, right? Now we also know Q over del T is Ka del T over L, right? So to find the gradient, the gradient, what we can do is we can plot, for example, if we get a linear line here, which we should do, we should get a linear line, right? The gradient here, and this will be all over time, be over del T. Now we have to compare this to our temperature, so P over del T, del T. Oh, okay, P del T be because power is energy over time. So energy is just PT. So we can just say that Q equals P del T. So we can maybe just plot Q here. But whichever quantity you measure, for now we're saying it's P. So our K would be P over del T would be that it's K A over L, right? We're assuming that this power, we're assuming that's the power or del T. Now, get the gradient. The gradient here would be Ka over L at a certain point T. We're assuming we'll assume del T, and then K would just be L over A times gradient, and we have our K now. This will be more accurate, right? So that's one way of fixing the solution. Now, the question also asked us, what are your potential outcomes, right? Describe the potential outcomes. So, for example, now we got a better value of K. Now, it could either be lower or higher than 0.5. So, if K value is larger than 0.5, that means that our heat transfer, our theoretical heat transfer rate will be closer to the closer to the 142 watts per meter measured value, which would decrease the discrepancy. That's it. Vice versa also applies. Okay, so that's one way of doing it. Now, what about our part? So we also talked about our transient heat conditions that could be an issue. Well, how or why does that affect us, and what would be the results? How can we mitigate this? We can say that just simulate transient conditions. conditions using ANSYS of in soil and oh wait ANSYS in soil, and then we just have to compare the time because this is through time, right? We're as soon as we time dependent time depend oh I'm not time dependent, I don't know what I'm talking results with measured data. Okay, now for example, just to make you understand what that means is, for example, maybe initially, so initially you could, so let's say at time t equals 0, that we have 168 degrees, right? We might have a different heat transfer rate. So Q prime could be higher than when it was going all the way down to 5 degrees. Maybe it reached a lower Q value here. It reached maybe a steady state around here. So this is maybe steady state here. And maybe it's transient here, you know? So because of this factor that we did not account for, we assume in steady state that this might change. So just using some analysis, we can find the k value, right, might lead to a lower steady state. So what we can say here, if, so let's go back to our typing here. So if transient, I'll change the color later, conditions effect, conditions effects are significant, then we can say that this might cause, which I said earlier, cause a higher initial rate, initial heat transfer, and then lower to the steady state. So we did not account for that. So maybe that's why our k prime value is a bit smaller than it should be, right? Because our q prime value is smaller than it should be. Okay, so this is enough for if you're content with this, you can just submit all this. I'm going to add a bit more stuff, a bit more detail into our K analysis, our soil variation, because we can say a bit more about this over here. So what can we say about this? So for example, a study was done. Let me change the color back to black. A study was done by the faculty in 2024. Our dean, Saad Ghani, Dr. Saad Ghani, Uh, he did a he did a study which was about a ground to air heat exchanger. Heat exchanger. Now, in this experiment, he what was calculated, I'll add an image here just for reference. So if I add an image here, he did it so that, for example, so this is what he got. What happened was that over here, let's leave it here, cancel. Now let's go back to our over here. Okay. What you can see is that below are the figures or plots for varying temperatures of air, of pipeline in air versus underneath underneath the ground. Underneath the ground. Now, let me to understand this. So what happened was, what they did was they uh, they had a pipe that went. That is a bad drawing. Let me just. So this is the pipe they had. Okay. And this they moved their height. So for example, if this was initially, so they're moving this height up and down. Okay, so this is, imagine, if you can imagine, this is ground, this is air, and they're varying the depth. They're varying this depth here. Let's call this depth y meters, yx, right? This is y of x, where x is the thing we're changing. Okay, so what they found out is that as you decrease the depth, sorry, increase the depth below the ground, you see that the difference between temperature, the peak values, are very low. So as they're going down and more further down, the peak values compared to the air significantly different. Now, what that means is your moisture content is also increasing. So moisture content of the soil increases. Okay. Now, in this study, what was done is they assumed that K for soil is equal to 15 point, what was it, 15.625? Yeah, 625 from the study. Y, where Y is the depth, right? So where Y is the depth. And then they also assume that at a depth, at a depth of more than 320 millimeters, K they assumed is 5 watts per meter Kelvin. Meter Kelvin. Okay, that's what they assumed. Okay, that's what they assumed. So it's watt per meter, right? It's thermal conductivity. I don't think it's no, no. I think it's watt per meter Kelvin. Yeah. Okay. Okay. So that's what they assumed. Now, with this, they assumed this using a formula from a book called from Faruqi, from Thermal Properties of Soil by Faruqi. So by Faruqi. This is what they reference, Faruqi. Now, I will now show you the figure they use to determine this K value, which we will use now to see if we can get a better K value or not. Okay, so this is what they have over here. And I'm maybe going to add another page here just to see if we can. So you'll notice that there are a couple of things we have to understand here. So what they're doing is they have, so let me go back to my pen. So sorry, my pen. Okay, so we have our pen here. So we need to get Ksat, K dry, Ke, and K dry. That's what we need to get. And for this, we need our dry density of soil. We also need porosity N. So this is maybe I'll write here porosity N. And we also need our particle thermal. So that is particle thermal conductivity, which is Ks. Thermal conductivity. We have to assume this for Qatar, which we would do. So Ks, which we need to assume as well. Anything else I don't think we need to assume. So if you look at some table values for K, for example, for these some questions we need to ask ourselves is we're in Qatar. So what type of soil content do we have over here, right? What can we say, or what for example are some things we could talk about? So some things that we need to ask ourselves is, so I'll add the thing over here is our soil coarse or fine? Is our soil frozen or unfrozen? I mean, not that one. What matters is also the dry density. What is our dry density? What we talked about. What's our porosity? What is our degree of saturation, which I missed, which is SR? And our thermal, thermal conductivity. Okay. So with this out of the way, we can try to answer, assume some things that we can help to get a better K value. Now, what we can do here is, for example, you know, assume a dry density. So this gives us, for example, let's check another one. Okay, so yeah, so let's assume, for example, for our dry density, it's a range between 500 and 700. So let's assume that it's around 1600 kilogram per meter cube. Okay. Now for this, the other one we're going to do is, what the other thing we can do here is this R that we need is around 15%. So it's around 0.14, 0. Sorry, 154. It's around 0.154 for, sorry, for SR, not one, for SR. I didn't write that down. So degree of saturation around 0.154. It what means is 15%, which is for dry fine soil. Now, what about our N? Our N here is that we assume here is around 0.35 for dry sorry, for fine soil. For fine soil. Okay. So now with this out of the way, we also have to get KS. So KS is around, for example, if you just search online, what would KS be? And that would be around 3 for solid thermal. That's around 3. Okay. So now with this out of the way, let's calculate some of these values. So we have our K dry, right? So K dry is equal to, we have 0.137 uh, uh, density plus 64.7 over 2,700 plus 0. Minus 0.947 1,600, and this gives us around about a value of 0.39 watts per meter Kelvin when you do the calculations. So after this, we can work out for K. This is for dry. Now for K sat, the formula we're using is this one, right? For K sat is K sat. Where's it gone? K sat 2.2. This one 2.2. So what we can do is 2.2 times Ks times uh yeah 2.2 n. Sorry, let's go back. 2.2 n. Sorry, 1 minus n. 1 minus n to the power n Ks. So just by looking at KSAT, so for just putting in values that we have over here, we should get around about an answer of 1.72 watts per meter Kelvin. And for KE, we assume that it's SR, so just log of 0.154 plus 1, and get a value of approximately 1. We get that it's 0.188. So it's around 0.188. Okay. Now with that's done out of the way, now we can calculate our K. Our K would be K sat plus minus K dry multiplied by 0.188 KE minus 0.3, is it 39? Is it? Yeah, 0.39. And we get an answer around 0.64 watts per meter Kelvin. So we just now try to calculate the Q prime again. We had earlier it was 1.37 times by 0.64 times by temperature from 168 minus 6. So we have our calculator on our hand. So if I now just go back to it. So all we're going to do is just press this as equal. And oh wait, this one. Hold on. Okay. And I want this to change to, for example, change this to 0.64. If I go up again here and press equal, I get around 140.74. So we get 140.74 watts per meter Kelvin. So this 140 watts per meter Kelvin is much, much. Well, I'll do it. I'll just type it up and see here. This new theoretical theoretical Q prime value is much closer to 142 just by changing the thermal conductivity. Changing the thermal conductivity of the soil. So this is just some things you can talk about. Like you don't have to maybe even go into detail. You can just write, for assuming a different K value of 0.64, you'll get this value because the range of the the range of soil uh, thermal conductivity varies with temperature. So the temperature and goes from 0.5 to 5 watts per meter Kelvin. Okay, so you can just mention that, and I think that should be fine as well. All right, good luck for your special assignment, and I'll see you next time.